AP Calculus 5-6, and we're going to find concavity of functions over their domains. This method is going to be very similar to how we used the first derivative test to find where functions were increasing and decreasing, and then we went on to find where we had maximums and minimums by comparing where increasing and decreasing changed direction. This is very similar in that we find concavity based on the second derivative. So we will set up our intervals again, but instead of setting them up based on increasing and decreasing in the first derivative, we're going to set them up based on the second derivative. So we're going to find the second derivative, and then we're going to set up our chart for the intervals, and then we're going to compare where concavity is changing. The point where concavity changes is points of inflection, and you should have talked about that in pre-calculus a little bit, but basically if you have a graph, and let's say the graph looks like this shape. I mean, this is obvious. This side is concave down, and it's obvious that this side is concave up. There is a point in here somewhere where the concavity changes. It changes from concave down to concave up. And at that point, and I'll just estimate that it's about right there, that point is the point of inflection where concavity actually starts to change. And we're going to be able to find that using the second derivative and comparing our values on a second derivative chart using the intervals. So just a quick review here. We can determine when the function is increasing and decreasing based on the first derivative. If f prime is greater than 0, then the function within that interval is increasing. If f prime is less than 0, then the function is decreasing on the intervals where f prime is less than 0. Where those changes occur, where it changes from increasing to decreasing or from decreasing to increasing, you will have your relative extrema, your maximums and your minimums. Now, a function is understood to be strictly monotonic. This is just something that I didn't mention earlier, but it's strictly monotonic if it's increasing or decreasing over its entire domain. And that can happen. You can have points of inflection when that happens. You might have something like this, where the function is continually increasing, but you can see it's concave down here and concave up here. So you do not necessarily have to have maximums and minimums in order to have a point of inflection or a concavity change. So I wanted to make sure I pointed that out. This one is increasing over the entire interval. It's possible to have a function decreasing over the entire interval, where you won't have maximums or minimums, but you could possibly have points of inflection because concavity changes from concave down to concave up or vice versa. Concavity is determined by f double prime. If your f double prime is less than 0, then your function is concave down at those points. If f double prime is greater than 0, your function is concave up for those points. So we use a first derivative test to find our relative extrema and where the functions are increasing and decreasing. We use a second derivative to find where the function is concave down and concave up. Okay, so we're going to use second derivatives. This is not called the second derivative test. The second derivative test still tests for increasing and decreasing, but we can use the second derivative to test for concavity changes. So I'm going to show you how to do that in the next segment. So here's our first example. It says find all points of inflection and intervals where the function is concave up or concave down. Now, I could find where the function is increasing and decreasing. I could find the relative maximums and minimums. I could do all that, but it's not asking me for any of that. All it's asking me for is where it's concave up or concave down and to find where points of inflection are. So I'm just going to go straight to my second derivative because I know the first derivative tells me about increasing and decreasing, but the second derivative tells me about points of inflection and concavity. So I don't even need to worry about doing anything with the first derivative. I'm going to go straight to the second derivative. Okay, so in order to get the second derivative, I do have to take both of them. So f prime of x is 4x cubed minus 12x squared. And then f double prime of x is 12x squared minus 24x. Just like before, when I was finding where the function was increasing and decreasing, I set the first derivative equal to 0. To test for concavity, I set the second derivative equal to 0. So a lot of these methods are going to be the same. You're just doing them with the second derivative instead of the first. So if I set that equal to 0, I'm going to factor out a 12x. When I do that, I have x minus 2 left. And so x equals 0 and x equals 2 would be the values that are I'm going to use within my intervals. So if I set up my chart using these intervals, the first one goes from negative infinity to 0. The second one goes from 0 to 2, and then from 2 to infinity. So we set our intervals up just like we did for the first derivative test, but now we're going to test the second derivative. I'm going to choose a value within the interval. So here I'm going to choose -1, I'll choose 1, and I'll choose 3. And now since we're testing for concavity, concavity is tested based on the second derivative. So I'm going to plug these values in to the second derivative. Again, I'm only interested in whether it's positive or negative. I do not have to find the exact value, just whether it's positive or negative. So when I plug -1 into the second derivative, and I'm just going to plug it in right here because I can get a simple positive, negative, negative, positive, whatever it is there. So -1 times 12 is a negative, and then -1 minus 2 is a negative. So negative times a negative is a positive. When I plug 1 in, I have positive times a negative. So that'll be a negative. When I plug 3 in, I have positive times positive, which would be a positive. So I'm only interested in the sign. I do not need to find the exact value. So what this is telling me is this function f is concave up when x is less than 0. So on the interval from negative infinity to 0, we have it's concave up. It's also concave up on the interval 2 to infinity. This function is concave down on the interval from 0 to 2. Now, the justification for that. I'm going to say the function is concave up from negative infinity to 0 and 2 to infinity because f double prime of x is greater than 0 within that interval. So it's concave up because the second derivative was greater than 0. That's my justification. And the function is concave down when f double prime is negative. So that's the interval from 0 to 2. And that is because f double prime of x was less than 0 within that interval. So we have named where the function is concave up and concave down, and we have justified that by saying that that's where the f double prime is positive or negative. Then they also ask us to find points of inflection. Points of inflection for this graph is where concavity changes. So we can see here that concavity changes from positive to negative at 0 and from negative to positive at 2. So the points of inflection, we have 2 of them. We have the point where x is equal to 0, and we have the point where x is equal to 2. To find those points of inflection, I do need to plug 0 and 2 back into the original function because they asked for the points of inflection. They did not ask for the x values of the points of inflection. So when they ask for points of inflection, then we need to find the points, the x and the y value. So if I plug 0 into the original function, I get 0. If I plug 2 into the original function, I end up with -16. You can use your calculator to find those values. So our points of inflection here are 0, 0, and 2, -16. For the next example, the derivative is a little bit more complicated here. So we're going to use the product rule with the chain rule within that product rule. So they're not always going to be real easy to find the second derivative. I started with an easier example. We're going to move into one that's a little bit more difficult now. So the first thing I'm going to do, again, is find the second derivative. In order to do that, I have to find the first derivative. So f prime of x, I'm going to use the product rule. The derivative of the first thing is 1 times the original second plus the original first times the derivative of the second. That's the chain rule. So that's 3 times x minus 4 squared. The derivative of the inside is 1. So that is my first derivative. I could simplify that a little bit If I consider this being the first thing and this being the second thing, I can bring out an x minus 4 squared from both of those terms. So if I do that, I have x minus 4 squared. Left on the inside, I have an x minus 4 plus a 3x. So the simplified form of f prime of x is going to be x minus 4 squared times 4x minus 4. The next thing I need to do is take the second derivative. Again, I'm going to use the product rule. So f double prime of x, using the chain rule here, the derivative of the first would be 2 times x minus 4 to the first times 1 times the original second, 4x minus 4, plus the original first, x minus 4 squared, times the derivative of the second, which would be a 4. Then, similar to the last one, I can, if I use, this is the first thing, this is the second, they both have an x minus 4 in common and they both have a 2 in common. So I can bring out a 2 times x minus 4. When I do that, I have 4x minus 4 left, plus an x minus 4 times 2. So I have a 2x minus 8 times, let's see, that would be a 4x minus 4 plus 2x minus 8. So I have a 2x minus 8 times 6x minus 12. So that is the second derivative. In order to find my intervals for my chart, I need to set each of these equal to 0. So if I set 2x minus 8 equal to 0, I have 2x equals 8, which gives me x equals 4. If I set 6x minus 12 equal to 0, I have 6x equals 12, which gives me x equals 2. To set up my intervals, I'm going to use these values as my critical values for the second derivative. So I'm going from negative infinity to the smallest value of 2, 2 to 4, and 4 to infinity. I'm going to choose a value within each of these. So I'll say 0 here, I'll use a 3, and I'll use a 5. I'm going to plug those values into the second derivative. I'm going to plug them into the second derivative that is factored here. So if I plug 0 in, I end up with a negative times a negative, which will be a positive. When I plug 3 in, I end up with a negative times a positive, which would be a negative. When I plug 5 in, I end up with a positive times a positive, which is a positive. So this function, f of x, is concave up on the intervals negative infinity to 2 and 4 to infinity, because f double prime is greater than 0. F of x is concave down on the interval 2 to 4, because f double prime is less than 0. So that's my justification. My points of inflection would be where the concavity changes sign or changes direction. So points of inflection would happen at 2 and at 4. And I can plug those values into the original function. So if I plug 2 in, I have 2 times negative 2 cubed is negative 8. So negative 8 times 2 is negative 16. And then if I plug 4 in, I'll have 4 times 0, which gives me 0. So my points of inflection are 2, negative 16, and 4, 0. Now, keep in mind, they could always ask you to find all of the information that we know. They could ask you to find where the function's increasing and decreasing. They could ask you to find all the concave up, concave down, points of inflection, relative maximums, relative minimums. Normally, they give you things, they don't ask you to do everything at once unless they want a graph of some sort. But in that case, they don't necessarily ask you to find everything algebraically. You can find them using whatever method you have available to you. But this gives you an algebraic method way of finding all of these important or significant values of a function without having to graph them. So far, all of the examples that we've done, we haven't had any asymptotes within the graph, and so I want to make sure you understand what happens if we have asymptotes in the graph, because we have to consider what the graph would look like at some specific points. It may appear that we have points of inflection or relative maximums, minimums at those asymptote points. So we have to understand and use our knowledge from Algebra 2 and from pre-calculus to keep us from making common mistakes with these. So I'm going to do one here. Notice, if I were to graph this, the first thing I notice here on the bottom is that I'm going to have some vertical asymptotes, because if I set the denominator equal to 0, I'm going to have x equals plus or minus 2. So I know I'm going to have a vertical asymptote at -2 and at 2. And so when that happens, sometimes within our second derivative, it's going to appear that we have points of inflection where our vertical asymptotes are. And so we need to be very aware of what's happening with our graph so that we don't make those mistakes. So I'm going to walk through this one, same directions. We're going to figure out where it's concave up and down, and then we're going to find the points of inflection. Okay, so I'm going to first find the derivative. I'm going to use the quotient rule here. The derivative of the top is 2x times the original bottom minus the original top times the derivative of the bottom. And that's all over the bottom squared. Then I'm going to simplify that top a little bit. Let's see, that is 2x cubed minus 8x minus 2x cubed minus 2x. And then if I simplify, the 2x cubes are going to cancel. So that's going to leave me for f prime of x. On the top, I have a negative 10x all over the x squared minus 4. So that leaves me with negative 10x over the x squared minus 4, and I did forget to square that. So that bottom has to be squared for the quotient rule. And then for f double prime of x, I'm going to take the second derivative, and again, I'm going to use the quotient rule. So if I do that, f double prime, the derivative of the top is negative 10 times the original bottom minus the original top times the derivative of the bottom, and I'm going to use the chain rule there. So that's going to be a 2 times x squared minus 4 to the first times 2x, and then that's all over, again, the bottom squared. So that'll be to the fourth this time. So to simplify this a little bit, I can bring out, let's see, a negative 10 and an x squared minus 4. So when I do that, I have an x squared minus 4 left for this term, and then here I have a 4x times x, so a 4x squared, and that's still all over x squared minus 4 to the fourth, which means this will cancel with one of these, leaving me with a cube there. So I have f double prime of x equals negative 10 times negative 3x squared minus 4 all over x squared minus 4 cubed. Okay, so I'm going to take this information. Here is my f prime, here is my f double prime. I'm going to write these down and get rid of this work so that I have room to make my chart. Okay, so the next thing I need to do is take my second derivative and set the numerator and denominator equal to 0 and set up my chart. So when I set the numerator equal to 0, well, the negative 10 is going to cancel out. So I'm going to have negative 3x squared equals 4. So x squared equals 4 over negative 3. So that's going to give me imaginary numbers. So I'm not going to yield any critical values with this one. So that's not going to help me. I'll throw that out. When I set the denominator equal to 0, that gives me plus and minus 2. Now remember, those were where my asymptotes were. We can still set up the chart because we're testing for concavity at this point. So these are significant numbers. They're important for us to understand that they need to be in the chart, but we need to understand that they're not going to be defined within the graph of the function. Okay? So if I do this, my intervals are going to go from negative infinity to negative 2, from negative 2 to 2, and 2 to infinity. I'm going to choose maybe a negative 3, a 0, and a 3 here. And remember, this is the second derivative that we're testing for concavity. So we need to plug these into the second derivative right here. So if I do that, if I plug negative 3 in, let's see, I've got a negative 3 here. Let's see, that would be a 9, negative 27 minus, so a negative times a negative would be a positive on top. And then on the bottom, a positive on bottom. So positive over a positive would be a positive. If I plug 0 in, 0 here is going to give me a negative times a negative, which is a positive on top and a negative on bottom. So that's going to be a negative. If I plug 3 in, I'm going to have a negative times a negative, a positive on top, and positive on bottom. So positive over a positive is a positive. So it's concave up on the interval negative infinity to negative 2, and concave up on the interval 2 to infinity, and it's concave down on the interval from negative 2 to 2. So we can justify that using what we used, or what we did here with the second derivative. So if it asked me to find where it's concave up, the function f is concave up on the open intervals negative infinity to negative 2 and 2 to infinity, because f double prime is greater than 0 for those values. F, the function f, is concave down on the interval negative 2 to 2, because f double prime of x is less than 0 on that interval. And then it also asked me to find the points of inflection. Okay, so it appears from our chart that we might have a point of inflection here because it changes from concave up to concave down and from concave down to concave up. But we do need to consider what's happening at these x values. Since those x values are undefined on the original function, we cannot say that they're points of inflection because those are in fact asymptotes. So basically what we've got here is we've got a graph, and at 2 and at negative 2, we've got asymptotes. We know that our graph is concave up on this side of negative 2, and it's concave up on this side of 2, and then it's concave down between 2 and negative 2. So it's going to look something like that. We don't know exactly what the graph is. We'd have to do a little bit more investigation, but that is not a point of inflection because the graph is not continuous there. So this is one of your special cases. I just wanted to make sure I showed you that. You have to consider where the function is undefined in the original f value, because if you have asymptotes there, those asymptotes cannot be considered points of inflection, but they might appear to be in your chart. So you have to consider what you've already learned and know that those rules do still apply.